graduate. He was the recipient of Significant Contribution Award 2013-14 from Computer Society of India. And he also involved in projects and completed projects on design and development of secure Stego system. And the recent, now he is involved in the project as a principal investigator, the project named Design and Development of Artificial Neural Network-based Expert System to diagnose human brain tumor from CT scan and MRI images. This is a brief, very short introduction about Dr. Mondal. And apart from this database, he is a very fine man. I know him as very interesting and fine man. And I would very much like to welcome Dr. Mondal to deliver this lecture. Welcome, Dr. Mondal. Please deliver the lecture.
Thank you, Arindan sir, and Kamalda. We call them Dada and all. So that apart from official designation. And good afternoon, good evening to all the participants who have joined this session. Okay, and I choose this topic because in our university, many people have very vague idea regarding high performance computing. So at least gradually through this kind of session, we must clarify the idea, the fundamentals, gradually to our scholars, students, and all the faculty members even. So I choose this topic often to share if anything happens in the university so that everyone knows and their conception gets clear regarding the high performance computing. This will be a little bit of technical talk, but I have lot many slides. But I'll be very fast. And meanwhile, if anyone has any doubt, please don't wait for the last session, okay? Just stop me and in between be interactive and ask questions, because otherwise the purpose is not solved. So I expect that you will stop me whenever something you have any doubts or you want to share with me. Please to stop me at that point of time and ask me, then we'll go forward again in that way. So again, I welcome all of you in this session. This will be like fundamentals of high performance computing, where from the starting to general traditional computers, we'll go gradually to what is the present state of the art and what will be the different kind of programming issues and how to program these computers. Although if you are not very much familiar, you may not understand each and everything, but I'll try to make this sure that it's very in a simpler form, so that everyone can understand, at least have their brief idea that what these things are and what it's not. So let's start. And before that, am I audible clearly?
Yeah, perfectly.
Okay, then thank you. And I don't keep anything in the topic slide because then we get very boring by seeing that, oh, a lot many things we have to cover. No. So we'll find this gradually, slide by slide. And I said in the very beginning, I have lot many slides, but it will not take time. Only to give you a little bit of idea, fundamentals. I have included many things in the slides. Let's start with some kind of applications that we are having in present days as a challenging applications. Okay. So these are simply called RMS applications, where the basic purpose is from some kind of images. That image may be any GIS image, that may be some medical image or something, from where we have to recognize some patterns. That pattern may be for tumor, that pattern may be for any kind of other disease or dislocation of any bones or something, or broken up bones. So from this image, we have to recognize whether something is there. If there, then what is the exact location or something. And we have to accordingly synthesize that whether it is how frequently it is getting enlarged or something. If this is the case, how frequently, how long should we go for treatment or something, what should be the treatment strategy at all. So these are a very commonly field where high performance computing is used nowadays. Similar, we have lot many other application domain like game physics, movie physics, then in share markets for financial analysis and all these things. Then in other kind of retracing based rendering applications like gaming and all. Okay. So this I'll just go through to give you a brief idea that there are some fields like in computer vision, image processing in virtual world, like 3D and all. Then processing of video or data somewhere that is available. In the field of bioinformatics also, like the human genome projects and everywhere. In case of geology, for earthquake prediction or something like that. And in the industry also for modeling, different kind of maybe cars or some aircraft or something. But for modeling also we require the computers to be used, and this application requires some huge amount of computational efforts. So it's a huge area or application domain where parallel computers or high performance computers are used, starting from your biology to physics to chemistry, even for numerical simulation in medical, for in the field of different engineering and other application domains in the field of computer science, in the field of oceanography. There's lots of application domain where this kind of computers are used. So what we have seen so far that we have a large number of applications that requires huge computational power to be involved to find some kind of solutions, and which are beyond the capability of present desktop computers or laptop computers, whatever you have in our laboratories in general. So this is one observation that we have lot many application domain where our traditional computers are unable to provide you the support that they expect from the computational point of view. Second thing, we find that there are lot many parallelism here and there. Even if we find our environment, we will find lot many places where there are parallelism already exist. So we have to consider these two things in mind whenever we will be going further. Then the second observation is, depending on the application domain, the requirement of different applications are distinct. You cannot say like if we design a computer for this application, that will be a good design for some other applications. Someone requires very high processing and memory system performances. Some other application may require high throughput even. Some other may require huge amount of network bandwidth to be provided. So different application utilizes different aspect of parallelism or high performance computers that we are having. So two things, we have some applications that we need to solve, which were not possible long before, but as the time passes and development happened, now we are in a position that we can solve some of those kind of problems. And different problems have different kind of requirements. So one particular system will not work for each and every application. That thing also you have to keep in mind. So to solve this problem, we need huge computational effort. But our traditional computers cannot provide such kind of huge processing power or capability. So what to do? So that old cliche, necessity is the mother of invention, still remains effective and correct, that when we require something, then based on that we do some kind of development. So as we have lot many such applications which are not possible to solve using our traditional desktop computers or laptops, whatever we are having, we require some computers that will be having huge computational power. So this broad term, high performance computing, describes a set of hardware and software techniques developed for building computer systems capable of quickly performing large amount of computational tasks. So here, two things you have to, we should follow that. It's a set of hardware and software, both. It's not only a hardware or neither it's only software. And they will provide huge amount of computational power so that we can quickly perform huge amount of tasks that we require to solve for. So we required first computer, why? To solve computer intensive problems faster, to make some impossible problems that were not possible to solve earlier, to make these feasible nowadays, and solve large problems in same amount of time. It should not take any MRI machine to take the image and give a result to 10 days to bring out the report. By that time, the patient will go off. So we require the results to be in real time. And to improve the answers, the precision of the answers, we require fast computers to reduce the design time of different kind of applications that if you do using pen and pencil, it will take time. Rather, if you can have some kind of softwares, they will design in a faster way. And obviously, to gain competitive advantage, we require fast computers. But how to increase this computational power? It's not a magic, right? So we'll go through how can we increase the computational power towards solving this problem. So from simple computers, we are going to build high performance computing systems gradually from the very fundamentals, because all of you are not from the computer science background. Assuming that, I'll just go through the pinpoints or the basic structural issues or design issues where we must keep on pointing to improve the performance of the computer systems. And for that, we need to understand the very basic computer architecture, that what a computer is, how it is designed. And the basic design, we have two kind of architecture. One is hardware architecture and another is von Neumann architecture. And the von Neumann architecture was proposed during 1940s by a mathematician called John von Neumann. So basic difference in the both architectures, pictorially if you find the difference, the only difference is in case of memory. In case of hardware architecture, we have two different memory, one for the instruction itself, another for the data memory, but the data will get stored. But in case of von Neumann architecture, there you have only one memory where both the instructions and the data will reside together. And the basic component of the systems are processor, memory, and the data path altogether. And input-output system are very much insignificant for us when we are talking about high-performance computing, because this input and output depends on the human effort, how fast you can use the computer. But we are desperately wanting, or we desire that the computational power means nothing that you are reading some data, not that how fast you are displaying on the monitor or screen, but how fast you can do large number of computations. Because input will be taken once or twice, output will be produced once or twice, but you require lot many logic and arithmetic computation to be done to come to a conclusion, and based on that conclusion you will give some output. So our main focus will be to improve the computational speed. So here the three main things that plays the role is processor, means what we call the CPU, memory, and the bus system through which the data travels from one part to another of the system. So hardware architecture is very little interest, because nowadays this kind of architecture are not followed. All the computers that we are having nowadays even are based on the architecture, von Neumann architecture proposed even during 1940s. Still we are having that. So the performance depends on how fast we can fetch the instructions that will be done by the CPU. How the data supply to be increased, that for that responsible is your memory. So we have to speed up the memory. And the processing power, doing some calculation, arithmetic or logic operations, we need to speed up the CPU. And for the data movements, we require to improve the bus system or data lines or control lines, whatever. So these are the scope area where we can do something so that we can increase the performance, because these are the primary component of any systems. So how to improve this performance? We have two approaches. One is hardware-based approach, that from hardware point of view, what we can do to improve the performance. Another is from algorithmic point of view, that we call like it's a set of hardware and software. So from algorithmic approach, we have to give some alternative solution to the problem, while using the different improvement in the hardware sectors, so that we can utilize this hardware for solving the problem. So we have to rethink about the solution strategy, as well as we have to improve the computational power if we want to improve the performance of the system. So from hardware based approach, what we can do in case of hardware, we can either improve the technology, or we can improve the architecture of the computers, or we can apply some kind of parallelism at hardware level. We'll see all this gradually. So in case of hardware improvements, generally this role is played by the Department of Electronics, and mostly now digital electronics. Analog is gone, and semiconductor industry. So successful research in the field of electronics and digital electronics and semiconductor technology, what we have done is, earlier we used to have the ICs at a very larger size, and nowadays due to the development in the semiconductor industry, all the components has become very small. And what is the result of this? Within the same area, now we can put lot many logic circuits all together. So the transistor density per unit area has increased drastically, and much more number of such transistors means large number of logic circuits you can embed, and that will faster the processing capability of the circuit, maybe in redundant mode or maybe in some other logics that will go through. So we have gone to higher level of integration in the circuits. So from vacuum tube we have moved to transistors, and from transistors we have moved to ICs, from there to small scale integration, from there LSI, from there MSI, then VLSI. Now we are in the era of system on chip. So chip technology is nowadays so advanced that we are about to close in 1 billion transistors on a single chip nowadays. So earlier the size of a transistor is now the size of a processor nowadays. So because of this higher level of integrations, we can make the circuits in a compact way with lot many circuits together to be used for purposefully to improve the performances. So this transistor per processor transistor allotment or transistor count, you can follow up that year wise. Whenever the new processors are coming and the number of transistors employed and the area remains constant almost. So much more number of transistors we are now able to put within the same circuit, and we have to utilize these transistors purposefully to improve the performances. Second improvement is we can do in case of improving the clock frequency of the processor itself. So if we just statistically go, the first processor that was proposed by or launched by Intel was 4044, that has only 470 kilohertz of frequency. From there, if we have moved up to Pentium 4, which has 3.4 gigahertz approximately stable clock frequency. Now, more the clock frequency means, if you consider at each and every frequency we can do one operation, then much more frequency is within the same amount of time we can do much more number of operations. That may be per second, that may be per microsecond, whatever the time unit is. So when we improve the clock frequency, then we can assume that per unit time duration we can complete one operation. So much more frequencies means much more number of operations we can complete within the same amount of time. So gradually you can follow up that the frequency from some kilohertz to some gigahertz we have gone through. So huge drastic improvement in the clock frequency rate. And we can check out the frequency how they have increased. So on an average 30% clock frequency is increased per year, at least up to 2010. So that is one reason that we are having now faster processor. But what happened suddenly during 2010, that the clock frequency improvement is almost stagnant. There is no further improvement in the field of clock frequency increase. Stable one, 3.6, some processors, but those are not very much stable one. But beyond 3. But stable one is 3.4 gigahertz that we get generally, lower than that even. But what happens suddenly that there is no further increase in the clock frequency of the processors. So the problem is, when we try to improve the clock frequency further beyond 3.4 gigahertz, it produces so heat the processor itself gets burned. So we are now stuck to the heat wall that we cannot go further in this direction, that we will keep on increasing the clock frequencies. So we are stagnant up to 3.4 gigahertz in that respect, from the point of view that will improve the clock frequencies, through which we will be improving the processor speed. Now what can be done? And you can just have a, for your idea, you can check out that what is the level of heat produced by any processor. Any Pentium processor produces heat nearby about a hot plate. And if we try to improve further, then it will go near about to a nuclear reactor. Beyond that, rocket nozzle or something like that. So after 3.4 gigahertz, we are stopped that we in this direction we cannot increase further because heat will be the problem. So now from there you can understand why the AC is there in the ATM. It's not to give you a comfortness, but it's for the computer that is installed in the ATM machine so that it can run for a long time without stop. Now what to do now? Is there an alternative way to speed up the processor? So Intel came out with a solution that in the same direction we cannot increase the clock frequency, rather we should go for multiple within the same chip. So that gives the birth of multi-core architecture. So far we had single core architecture. We have gone up to the zenith point of improving the clock frequencies. Further we cannot go. So the alternative now is, instead of increasing the clock frequency, we will embed multiple number of such processors together, but from outside it will look like one processor. And the first processor in this direction was Pentium M, where actually inside there was two Pentium 4 processor. From outside it will look like one processor. After that, Intel bring out a dual core processor. From there, Core 2 Duo. So two names synonymous some extent. Actually, there is some manufacturing problem with the dual core processors, but those are already manufactured, are already in the market. Intel didn't want that this kind of blame should come into their shoulder. They rectified in the further processing or manufacturing of the processor. They give Core 2 Duo. So from performance point of view, Core 2 Duo has almost 40% better performances than dual core. So now we move towards multi-core architecture. So use multiple cores all together on the single chip to improve the performances. So likewise, how many cores can be there? There can be thousands of core even. So much more number of core are getting embedded within the same chip to make it to improve the speed of the processor. Now, when that is also done, that the multi-core is also achieved, with that performance still we are not able to perform the solution that we require to solve to the problems. So we now put multiple such processors within the same system, and that is called your multiprocessor systems. So within the same motherboard, you will be having multiple slots for the processor. So these individual processors may be in a multi-core processors, but multiple number of such processors can be embedded. And this kind of computers are called multiprocessor systems. Now, with that performance, multiple number of multiprocessor system with multi-core is still insufficient to provide the performance that we want to solve this kind of large problems. So we have to improve further. What can we do now? Now we can use multiple such computers together to solve the problem, where each such CPUs can have multiple processors with multi-core in each. Likewise, we can connect multiple number of such CPUs together to look like, and they work like for a single system, and that's actually is what called cluster computing. So from single core to multi-core, from there to multiprocessor, from there to cluster computing, we are moving towards. So we are actually having this kind of a system. In the image we can see where n number of CPUs altogether are internally connected with a single IO devices, and this will actually truly a parallel computer, but still the terminology will remain like a cluster computer. So here you have achieved up to this amount, that n numbers of such CPUs having n number of processors, having n number of cores in each of such processors, we can build up this kind of systems. All the CPUs are interconnected via some switch or high speed networks so that they can communicate among themselves. And we can utilize all these CPUs, all the processors all together to solve one particular problem. This is truly actually the parallel computer is. So cluster computing is improving day by day because we have lot many significant improvement in the field of networking technologies. And because the networks are getting improved, so people are moving towards this kind of clusters. They, from during 90s onwards, clusters are started to came into picture. Any further improvements in this direction? Yes, we can now go for grid computing. What is grid? Such lot many clusters, they are geographically at distant locations, may be connected via dedicated network, so that now all these clusters will be working together to solve a particular problem. And this one cluster may be at Delhi, another cluster may be somewhere else, another cluster may be in Guwahati, but they are interconnected via dedicated computer networks. And this kind of computing are called grid computing. So what is the case in India? Just for that where we stand, the Indian government proposed a project called Garuda under the supervision of CDAC, Pune, and almost 45 institutes over the country. They are located at 17 different cities across the country, are connected via dedicated networks to build up a cluster computer like that, which can be used to solve this kind of larger problems. They have huge number of computational node, huge amount of storage to provide if required for. So these different cities all over the countries are connected with their cluster computer labs all together, so that if anyone requires, they can submit the job from one point. All the clusters will get involved in solving the problem together, and it will give you the first result on the output, as an output on your output screen or as a data or whatever. So this is something called supercomputing. So it's not a very other terms, it's like the same terms where large computer within an architecture that has been optimized for bigger problem solving in a faster rather than in a conventional desktop or mainframe computers are loosely called supercomputers. And here basically pipelining is used extensively and parallelism is used extensively. So this is taken from internet just to give you an idea that all these all together, the entire rooms is actually a cluster. All these kind of racks looks like Godrej. All are CPUs all together internally connected. So all are working together to solve one particular problem. So that was from the point of view of improving the hardware and the processor itself from a hardware point of view. In addition to that, now we have to improve the memories also, because the data and the instruction will reside in the memory, and for computational purpose, the CPU should be kept on feeding the data at a regular interval rate at the frequency where the CPU can work. And still, whatever the amount of memory, whatever the memory technologies are available, still from frequency point of view, there is a gap of 40% speed mismatch as compared to the processor and the memory at which it supplies the data to the CPU to do some kind of operations. Means almost 40% of the time your CPU remain idle because the data is not available with the CPU on which it will do the operations. So that gap has to be minimized drastically. Otherwise, just improving the microprocessor will not do the work because the data has to get supplied from the memory system. And nowadays, we are getting SRAM and DRAM altogether in the available in market, but SRAMs are better as compared to DDR-RAMs or DRAMs, SDRAMs. Why? Because SRAMs are made up of transistors and DDR-RAMs are made up of capacitors because capacitors are cheaper. So huge amount of memory can be given at cheaper cost, but from performance point of view, SRAMs, static RAMs are better. And also consumes less power because transistor can hold the voltage level up to certain amount of time without refreshing. But if capacitors are used, then you have to keep on refreshing the power to retain the voltage level because they transmit the voltage to the environment very frequently. So we have to improve the technology for building the good quality of memory. At the same time, we have to increase the size of the memory where we can put lot many data, as we require huge amount of data to perform on this, and we want huge bandwidth so that large amount of data can be travel from one part to another at any instance of time. At the same time, we have to keep on reducing the latency of the memory so that whenever we give a request to the memory system, okay, give me this data, and the time at what it supplies me the data, this has to be minimized. That is what called latency. Another part of this was that we have to improve the bus system altogether. Bus system means through how different components are connected together through which the signal will transmit. So nowadays you are getting all the electronic devices like on single chip, system on chip. Why? Because the components are all together so closely tagged that the signal travel will take less time and also requires very minimal amount of power. The power consumption also keeps on reducing. In that way, in the same line, the one chip interconnect has increased significantly, due to which we are able to speed up the systems of the computer. So after that bus system, I am not going to very deeper of technology. I just give you the idea that where the key issues are remaining and where we can do some kind of modifications. Now we have to apply parallelism in somewhere. Be it in hardware or be it in software, we'll see, but we are now concentrating on hardwares. After doing all this, because the transistors have been very small in size and lot many transistors at a huge scale are integrated in the processor, now we can build multiple logic circuits within the same circuit, and based on that, as lot many elements are there, can we do something like pipelining to improve the performances? So we'll apply pipelining in architectural level in instruction fetching. The same thing can be applied in case of any arithmetic operation also. There can be instruction pipelining, there can be arithmetic pipeline also. So in a non-pipeline architecture, that was the case earlier. What used to be done, suppose that any instruction require 5 steps: instruction fetch, instruction decode, then suppose execute, okay, or opcode fetch, then execute, then store something. So for the time being, assume that 5 small stages are there in one instruction, and each such step takes t amount of time. Then to complete one instruction, it will require 5t. To complete another instruction, it will require additional 5t. So likewise, to complete 5 instruction, it will require 25t amount of time. Now in the pipeline architecture, if you follow downwards the image, what happens now? When one instruction is getting fetched, then the other sub part remains vacant. Now when the first instruction is getting decoded, by that time another instruction, because the fetching unit is now available free, second instruction is used to get fetched from the memory. The similar way, if we just keep on increasing the states, we can achieve some kind of parallelism in pipeline fashion. Now to complete that 5 instruction, you see the first output of the instruction will come after 5t time, but henceforth after each t we will get one output available. So now to get 5 instruction to get complete, we require 5t plus 4t additionally, mean within 9t we will complete 5 instruction. In the earlier non-pipeline case, we require 25t amount of time. But designing the circuit and all has become much more complicated. But we can improve this way the pipeline architecture to utilize the hardware available to improve the performance of the system. So nowadays, at least 64 such steps are followed in case of modern processors, so that we can achieve much more number of pipelining, and we will make each stage very smaller. So that way we can do multiple number of instruction getting executed, or the output of each instruction is coming after a very short interval of times. But the circuit design complexity remains your headache. Second, what we can do, we can overlap different operational units. Either we can have one control unit, under that lot many ALUs. ALUs means all the logic circuitry that will perform the job, and control unit will give the instruction what to do. So as you are having multiple such functional units like ALU with their memories, so at the same point of time, many instruction can be given to the multiple number of ALUs, and multiple such operation can execute in parallel. Similarly, there can be multiple functional unit of different logics. One will be for doing addition, another will be doing for dealing with the branch instruction, another maybe for floating point arithmetic operation, another maybe for integer kind of operations. So multiple such units are there. We can engage all of them in parallel to improve the performances. Obviously, with the cost of increase in the circuit design and additional cost of the circuits. Further, we can improve the speed by exploiting the data and temporal parallelism, like the case of array processing and vector processing. Multiple units of data can be given here. Further, to improve processor, what can we do now? Instead of issuing one instruction one by one, at the same point of time, we can issue multiple instruction to get execute if there is no dependency. Although that's not the case always, there are a lot many dependencies. But if those instructions which are independent to each other, we can issue to the CPU that two such instruction is given to the CPU to execute in parallel. And this kind of architectures are called superscalar architectures, where multiple instructions are getting executed at the same point of time. So pipeline is still there, but now instead of one instruction, you are given multiple sub instruction. For example, in the picture is given two such instructions is given on the same point of time. So that way we are improving with pipelining as well as multiple instruction at the same point of time. So this kind of architectures are called superscalar architecture processors. Further, what improvement is done? That instead of an individual instruction in one word, add multiple such instruction together and make a huge long instruction word. So multiple instructions are combined together. Now from the abstract level, it looks like only one instruction, but internally there are 4 or 5 instructions altogether. The CPU identifies all the different instructions. What advantage we get? Instead of going to the memory, take one instruction and give it to CPU, now we are taking at a time multiple number of instructions and giving it to CPU. So multiple times you don't have to come to memory for taking the instructions or data. So that way, we call this kind of architecture to be as VLIW architectures. So from single computer, we gradually move towards multi-core processors, from their multi-computer systems, from their clusters, grid computing. Cloud computing is separate, but I am not going to discuss here, like the supercomputing, all this. So that way we have improved from the architectural point of view. But using multiple computers is expensive and requires additional effort, hardware and additional support from the hardware also. So the designing of the hardware are very much complicated and it's expensive, so it cannot be given or offered to any desktop PCs within the budget that we have to purchase a laptop or desktop processors. So multi-core processors are, in compared to that, cheaper but slower. So what feasible solution for daily use can be done? That with all the laptops and desktop nowadays, graphics processing unit are coming as a unit. This is not supercomputers, but for traditional computers, we want to improve the performances for the commercial computers that you are having at your home or somewhere, the desktops. For processing the graphics, you have additional graphics unit that used to be called VGA card earlier. So what are these GPUs? These GPUs are nothing but like small CPUs, but having very low frequency, but at huge numbers. So now these are given for your image operation. Suppose you are playing games where it requires the each and every pixel to be simultaneously moved in a rotation or scale down or something. Then lot many operation has to be done at the same point of time. Otherwise, the movement of the elements like movies or something, it will not be so smooth. So with a cheaper cost, the GPUs are now given. Now you have the CPU plus you have the GPU. Can we use this GPU not only for the graphics operation but for our daily computational purpose? And this field is what called GPGPU, General Purpose Graphics Processing Unit, because it's available readily. You are not doing any game operation, but you have a graphics processing unit. Then can we use this GPU unit for our computational purpose, not for your gaming purpose or something like that, as these are readily available in your computer. So this field is called even GPU. So these are coming for desktop or laptops. So you can find there are n numbers of ALUs altogether. The control unit cache memory are like the same. In case of GPU and CPU, that may vary in size. But the fundamental difference is there that you have n numbers of small ALUs where they have their own dedicated control unit and cache memory, and the DRAM is your shared, which is cheaper one. So you utilize this for our computational purpose to solve these problems. So the serial part, if you don't have a parallel processor, the serial part can be executed by the CPU, whereas the parallel part of your program can be given to GPU to work in a faster in parallel mode. That way we can utilize the GPU to do our basic operations. So this kind of GPUs are nowadays readily available in the market. You just purchase it, insert in your PCI slot, or externally you can connect so that you can improve your graphics processing operations. So as we are, it's 7:45. I'll try to go further. There are some.
Okay, no problem.
So now what is then parallel computing or high performance computing? So in simple terms, we will use more than one computer or processor together to solve one particular computational problem which requires huge amount of computational effort. And that field is your parallel computing, that field is your scientific computing, that field is your high performance computing, that field is your supercomputing, different names in different places. Depending on the scalability of the application and the structure of the system, how big the system is, we give different names at different point of time. Or an interconnected set of processing elements, means the processor, which cooperate by communicating among themselves to solve the large problem in a very faster way. That's your parallel computing altogether. So to do this, we require to improve the interconnect technologies, which should be fast, reliable, and scalable at the same point of time, along with the improvement in the processor and the memory and the bus system. Fine. Now the data has to supply to the CPU at a very frequent rate. So how the memory can be organized when you have lot many such CPUs? Based on that, we can classify the computer architecture into shared memory architecture, where there is only one memory, and that same memory is accessed by all the CPUs all together. So individually they don't have memory, but they have to share the same memory. And there is two different kind of shared memory architecture. One is UMA. Each and every processor has equal access to the memory, whereas we can somehow segregate few CPUs for dedicated for a small amount of memory, few more CPUs for some another amount, where each and every processor has access to each memory, but their access time will be vary from one memory region to another memory region. That's your NUMA. In other case, distributed memory architecture, what is there? That for each and every CPU, you have dedicated memory for yourself, and those are interconnected together via the network, and they can communicate among themselves somehow. How we'll come to see in the next slides. And if you mix up all this architecture, then it's called a hybrid memory architecture. Now, just given lot many hardwares, but only one problem will not solve the problem. You have to give individual users the resource that they require to compete for. So this kind of first one, that you have lot many hardwares but only one application, will not work in parallel mode. If you have only one resource but lot many people, still it will not work. What you have to do? To optimum utilization, each and everyone should be given the resource so that they can do their job by themselves without waiting for the others to release their own resources. But are these all sufficient? That given all these kind of resources, hardwares, will we achieve the performance what we want? Definitely not. So there comes the programming considerations. That we have to have different approach towards solving this kind of problem given all these kind of resources. So in traditional sequential computing, what do? We have the problem, we decompose the problem into small instructions, and one by one the instruction is given to the single CPU, because the actual job will be done by the CPU, and one CPU at any moment of time can execute only one instructions. So in the traditional computing, we have one CPU, so it can only execute one instruction. Your big problem consists of several instructions. Now you take out each and every such instruction, keep on giving to the CPU, so sequentially it will get executed. So that is sequential computing. Now what if this is the case that you have the same problem, you have split it up into one instructions to be supplied, but you have lot many CPUs. Still, this is not a kind of parallelism, because you are giving the instruction one after another. So having 5 CPUs or 4 CPUs will not do the work. Or in the reverse way, if you have lot many instructions given at the same point of time, but you have only one CPU, the CPU can execute only one instruction, although given 4 or 5. So it will do actually in sequential way, although you issue multiple instructions. So truly, this is the structure of a parallel computer should have been, that you have a problem, split up into multiple instructions, supply multiple instructions to the CPU when your CPU have multiple processors. So that should be the nature from problem-oriented point of view, from hardware point of view also. So only having multiple such hardwares will do the problem in a faster way. It's not the case. So now it's coming the parallelism in case of softwares, where it actually plays by the programming. And how to achieve this? There is no silver bullet. You have to think by yourself. You have to have your own logic. You have to know what is parallel algorithm, how the problem should be solved in a parallel mode, whether it can be solved in parallel mode or not, because all the problems cannot be solved in parallel. So you must have a better language. You have to have better compilers, okay, library files and everything, tools for checking, correcting everything, because writing these parallel applications are typically tough. It requires lots of programming effort and algorithmic changes in your mindset, that earlier whatever the programmers are trained, they are trained to write sequential programs, but because of the hardware changes, you are now required to be trained to write parallel programs if you want to go for the optimization of your performances. So here is the picture of parallel programming comes into issue. What we can do for? We can extend the compilers that will write sequential program, but the additional burden will be given to the compiler that it will translate which part can be done in parallel, which part can be done in sequential way. The entire responsibility goes to compiler, but that is very bad approach. Extend another language, existing language, that you have some existing operations, add some parallel operation on that. Or you add a parallel language layer on the top of the sequential language to look it like a parallel language. Or the best way is you redesign programming languages also and the compilers also, so that we can write the parallel programs in a newer way. What is the current status? That low-level approach is very most popular, that you have to apply your own logic for writing the parallel. Don't give the responsibility to the compiler, because compiler is also written by someone. So that may not be intelligent enough to identify which part can be done in parallel, which part can be done in sequential. So you understand the problem better. You decompose your algorithm and you write the program yourself. Don't give the burden of identifying which part can be given to the compiler for identifying the parallelism. So disadvantage of this is it's very difficult and to write the programs and debug. But from efficiency point of view and from portability point of view, this is the best option, that you write your own parallel programs. So as we have seen, we have two kinds of memory architectures primarily, shared memory and distributed memory. Shared memory, as the memory is shared by all the processors, it's like that you have one table having lot many foods all together, veg, non-veg, and you sit in the four corners, and which one likes by anyone, he can take from the same table, but all the foods remain on the same table. So it's accessible by all the CPU when the data or instruction is in the memory. And this kind of memory model, if the system is having, then we should go for thread kind of approach, multi-threading programming for writing parallel programs. And there are two such standards. One is POSIX, okay, or pthread even called, and OpenMP, through which we can write this shared kind of parallel programming. But make sure that this kind of approach, one, you cannot change the memory from your machine. So these machines are not scalable enough. Tomorrow you have some money, you purchase one CPU and you want to attach with your existing parallel machine. So this is not possible. So rather, all the systems are coming like that cluster computers. And these are distributed memory kind of. You purchase one memory slot, one RAM, you insert in your PCI slot on the motherboard, you purchase one CPU, or you purchase another motherboard, you take some additional memory, additional processor, keep on plugging in the network system. So your system will keep on increasing day by day in size and from performance point of view. So all the cluster computers are generally distributed from memory point of view. And when this is the case, it means like there is one table with food where you have the vegetarian foods, another table where there is some kind of sweets, another table where there you have non-veg foods. So if you are sitting in a table, you want some food that is in other table, then the food has to travel from that table to your table via some mechanism. Either you have to go and put in your plate, or that food should be transferred to your table. So physical exchange of data will be there because they are residing into two different distinct memories. And to write parallel program for this kind of memory architectures, we have either PVM or MPI, and MPI is preferred over PVM, and MPI stands for message passing interface. And there are two approaches of programming even. One is SPMD, single program multiple data. Another is MPMD, multiple program of multiple data. So you follow the images. In SPMD, all the CPUs are executing the same program, abc.c. Whereas in case of MPMD, all the CPUs are working at the same point of time, but they have different programs in their memory. And this kind of things, MPMD writing programs is much more complicated because they had to communicate among themselves to exchange the data. And the programs are different. One computer 1 or CPU 1 is executing program 1, CPU 3 is executing program 5 or something like that. So different programs. So that's why it's called multiple program, multiple data. And whereas in case of SPMD, you write one program, the same program will execute with all the CPU, but each and every CPU will know which part is for me. Out of all the programs, I will execute only this part. The remaining part I will not get executed. So we'll follow SPMD model of parallel programming using MPI. So just to give an idea, I'll finish by time. Don't worry. So what do you know? What do we need to know? That what are the different amount of processors available? So we have to keep on grouping them. And the by default group will be your MPI underscore com underscore world. And these groups are called communicators. So only the processor belongs to a group can communicate among themselves, other cannot communicate, which doesn't belong to the same group or communicator. Similar way, same processor can belong to more than one group. And you can make multiple groups depending on the need of the processor, that how many processor you want to get involved for this computation purpose. So just giving lot many processors will not do the work. So this will be called communicators. Now, MPI routines means the libraries that we required to do this kind of programming. So we require additional set of functions which are not readily available in our C or C++. And for example, we will be following C only for writing the programs, but with additional features that we require that are available in MPI header file with the library functions. So what kind of need we have? We require to have some kind of communication mechanism between the two processors or among all the processors or among few processors. We may require to have different kind of process management group functions to schedule the processes accordingly and whom to assign which job, when to assign, when not to assign or something like that. And the different kind of data types also. And how this processor to be configured topologically. For that we require some additional function and some miscellaneous function for other management purpose. So I will not discuss all this, but you can just see that there is different kind of functions that are readily available. These are for only writing parallel programs. So what is the general structure of a program? And it's a C, and almost you all know C nowadays, because irrespective of any scientific department, everyone has a kind of programming language like C or something. So it's like a similar traditional program, but what additional thing that we have to include the header file mpi.h that is dedicated for these parallel routines or libraries to be used for writing parallel programs. Others is like the main function in C, and you have to initialize the MPI environment before starting the parallel part of job, and you have to terminate that MPI environment after finishing the parallel part of the job. The sequential part may be above initialization of MPI environment or after finalization of the MPI environment. And we have two functions. For initialization, we have MPI underscore init, and for finalization MPI underscore finalize. So that way, using some of these functions, we can write the parallel programs in C for these parallel systems. Now, suppose this is the simplest program we are having, and we are following SPMD model. Like this program will be in your memory, in my memory, in someone else's memory. So this same program will be executed by you also, me also, or someone else also. And we all belongs to the same communicator group. So each and everyone will print hello. And that is given. How do you understand that this is a parallel part? Because this printf function is within MPI underscore init and within MPI underscore finalize. By doing, after invoking that function init, it will do the MPI initialization in parallel mode. Then after that, whatever the instruction will get in parallel mode, after finalize, that will come to sequential mode again. So what will be the output? Almost if we try to execute this with 3 processor and see that commands for compilation varies from compiler to compiler. In GCC compiler in Linux, generally mpicc is the command used to compile the parallel program, and to run mpi run, and with that specifier you have to tell with how many processors you want to get execute this. So if I run this program with 3 processors, there will be 3 hello. If we try to run with 5 processors, sorry, here it will be 5, then it will be 5 hellos, depending on how many processors you are having in your system. So just to give that how within the same program, 2% can do 2 different things. It's nothing but within the communicator, each processor will get an unique identifier that you have to identify yourself by this kind of functions. Then based on that, if my rank means sub my ID is equal to 0, then I'll do some job. Like here I am, it's printing that I am master and my rank is this or that. Or others will do the other jobs. So each and every one belonging to the communicator will have their rank starting from 0 to n-1 if there are n number of processors. And by this ID you can segregate within the same program which part to be executed by me and which part to be executed by you, or which part to be executed by whom else. So that way the SPMD model works, that the same program will be in all memories, will get executed by all the processors, but each and every one will execute different part of the programs. So if we run this program with this, with 3 processors, it may come like this, the outputs. So from this programming point of view, I'm not going to discuss this because you may not get interest on this, but to just show you that okay, this way the programs are written in small examples. This is not real life examples. Okay. So what we come to know, and to write parallel programs for the GPU architecture, we use CUDA that was invented by NVIDIA. Fine. So I'm not going to discuss this. To finish up, what is the summary? That there are a large number of emerging applications that demand huge computational power. Parallel computers are designed to perform optimally. Not all the computers are parallel computers. Neither all the problems are parallel in nature. There are some problems which are sequential in nature. You cannot apply parallelism, and if you apply that same program, you will not achieve the performance. Parallel application need to be developed using parallel programming language and approach only. Neither parallel program will give better performance on a sequential computer, not sequential program will give better result in parallel computer. Hence, parallel application will give the best performance on parallel computers. So this is the kind of problem we are having, that we bring any program and try to execute on the parallel machine, HPG system, and we shout that why we are not getting the speed up. Because the program may be sequential in nature. So any program, if you try to run in HPG system and you expect that it will give you better result, no. You have to rewrite your programs in parallel mode, then only the parallel system will work. Otherwise, what will happen? Out of n number of processors available in the system, but only one will do the work. And only one with n number of processors, and having only one itself is of no difference, because all the others are remaining idle. So different applications have their different architectural demands. So we cannot say even like I have purchased this parallel computer, so it will work best for this application. So again, it will work best for the other applications. No, for each and every applications, as their demands are different. So we cannot say like you purchase a regular t-shirt and it will fit to each and everybody. Depending on the nature, you have to write the program differently. You have to use the different parallel computers with different architectures. And obviously, you need to write in parallel mode. Don't expect that you have a sequential program, you execute in parallel machine means that it will give you a huge number of performance effort. No. Even it's not the case that when you are going to write a program to solve a large problem, okay, or small problem, you write forcefully in parallel and you think that, okay, it will give best performance. No. Forcefully, if you write a sequential program to be in parallel, what will happen? For 1 second computation, the data has to travel 5 minutes. So the traveling time of the data movement between one processor to another processor will take much more time. Instead of that, you could have been execute that with lesser time with single processor. So we need to understand the ideas so that we can know that how the program should be written in parallel mode. It's a very brief idea. Okay, lot many technicalities are inside there. I try to skip to finish within the scheduled time. So there are some references, and thank you for your kind hearing. And you may always go to this website, and where you can find out that which countries are having which topmost or supercomputer or parallel computer at that moment of time, and what is their configuration, what is the number of cores. See, this Japan is having a machine having how many cores, what is their power, how much electricity they consumes, and where India is. And this list gets updated every 6 months. And this is the very genuine source of the information. We are there, if we search for India, we are at number 89 now, globally. And the parallel machine that we claim to be for that number is here, Param Siddhi AI. And these are the number of ports and everything available. And this keeps on changing. So what is the basic idea that we need to learn more to understand this parallel computing? We should not blame any system or a program. Maybe the program is sequential. We are trying to execute in parallel mode system, or maybe the program is parallel, but we are trying to execute in a sequential machine, and you are not getting the optimum performances. So with this, let me finish. And if you have any queries, you are definitely.
Sir, sir. Hello. Sir.
Yes.
Hello. Sir,
Should I stop the
question is.
presentation?
Yes, sir. Yes.
Okay.
Sir, regarding that CUDA, sir, and OpenMPI that we have seen here,
Yes.
sir, we are trying to actually run a merge sort, simple merge sort technique using parallel and serial computation.
Right.
Sir, but the thing is that when I am running in parallel mode, the execution time is taking very high than the serial one. Why it is, sir?
You have to check out whether
Yes,
that program is written in parallel mode or not. Unnecessarily, if we try to force
No,
parallel.
Pragma, sir, we have included the Pragma parallel, that particular directive we have used over there, sir.
Okay,
But
then
the thing, then sir, but when execution, I mean, when the data set is taking, we are providing it the data set. Actually, finally, we see that the execution time in the serial is much less than that of the parallel.
Exactly.
Sir, why it is? Sir?
Why so? Yes. A Pragma and OpenMP is used for shared memory architecture. It's a kind of multi-threading. Okay.
Yes, sir. Yes.
But it may be possible that the system you are having, that's a distributed memory architecture.
Sir.
Then it will not work. It will work, but it will not give the best performance.
Okay. Okay, sir. Then we need to run in the parallel machine only.
Obviously, if you want to take best performance.
Okay. If you want to exploit that parallelism.
Exactly.
Okay. And sir, one more, sir. Last question, sir. One
Yes,
more is there, sir. How, sir, is quantum computing different from all this, sir?
The quantum computing is just a new evolving field.
Yes,
Only on an experimental basis, some company from competitive point of view, they have claimed that okay, we have built, but that's not yet built enough.
oh, sir.
Where the basic philosophy is, instead of a voltage level, we'll identify 0 and 1 based on the spin direction of the electrons,
Okay.
and which is very calm, controlled. So still it is remaining in the experimental phase.
Okay. Practically not possible. Practically it is not there actually.
No. We have to see the future technical direction. If we can develop some mechanism that we can control the spin of the electrons, then if you need from the right side, then we can call 0. If you need the right side, left side, we can call it 1 accordingly. Then the power consumption will be very less because we don't have to reach to the voltage level.
Okay.
So the systems can be very smaller in size.
Okay, sir.
So much more speed can be there. Frequencies can be improved significantly if possible.
Okay.
Okay,
Okay, sir.
anyone else?
Hello, sir. Good evening. Hello, sir.
Yes, Santosh Nandi, please.
Sir, my name is Santosh Nandi.
Right.
For my question is that for message communication, we use a C programming. Can I use any C++ or any object-oriented programming Java for message communication?
Yes, possible. As we are comfortable with, and these are gradually coming now. With Pythons are coming.
Yes, sir.
With Fortran is there.
Yes,
Okay?
sir.
And all the programming language. See, as hardware is now became parallel by default in nature. So by tomorrow you have to shift to this parallel programming forcefully if you want to take the advantage of the hardware.
Definitely.
So the languages are gradually changing by the vendors or the forums to be used for writing parallel programs.
Sir, basically it's like a type of thread, multi-thread.
I cannot understand your question.
Sir, this parallel programming is related to basically multi-thread programming.
For shared memory architecture based, if your system is, then it's a shared programming. It's a threaded programming. And if it's a distributed kind of memory architecture, like the clusters, okay, then you have to go for message passing. So it depends on your memory architecture and your system architecture that for what you will write multi-threaded programming, or for what you will write MPI-based programming, or for what you will go for MPMD.
Okay, thank you.
Anyone else?
Ardhendu, there are some questions in the chat box. I am reading it.
Okay.
The question is by Animesh Bafra. What is the basic relation or difference between a core of a processor and a thread?
See, thread is a logical unit. Okay, for execution purpose is sequence in which the instruction gets executed. In a program, there will be multiple such sequence that one after this, if you group these instructions, it will become one thread. So it belongs to a program, but a program can have multiple such threads, and these threads will be logical unit of execution of instructions which are independent or dependent on that particular fashion. And each such thread and core is a hardware part within the processor. So each thread can execute at any point of time only one either process or thread, but logical speed up can be increased up to some level because threads share same memory. And if you, instead of a process having multi-thread, so same memory will be used by all the threads. But if you write like similar threads, 3 threads, if you write 3 processes, then for each and every process, the memory allocation will be different. So memory occupancy will be much more if you write multi-process as compared to multi-threads. And multi-threads is only possible when you have shared memory, because the property of the thread is they share the memory. They belongs to a process. The process will have memory allocation. For there, all the thread that belongs to the process will share the same memory locations. Is it clarifies your doubt?
Animesh, you can ask. Okay, you can unmute yourself and ask if it is clear or not. Animesh, are you there?
Yes, sir. Thank you. I have another question that is there any software or programming to use the GPU that you have said along with the CPU to make our computer as a super scalar computer like that?
Exactly possible. You have to blend with C and CUDA. And CUDA is like C kind of language only. CUDA, CUDA.
Okay.
That language is invented by NVIDIA, because in the field of GPU, NVIDIA is the giant along with like your AMD. So CUDA you have to learn.
Is there any instruction in the CUDA to use the GPU with CPU?
Yes, you can use. You can blend depending on your thing.
Okay, sir. And in MPI, message passing interface that you have said, I have tried that to do some parallel programming. Just I copy paste some programs that hello world something that was executed properly. But when I try to write another program within that, but it was some problem and giving much more errors.
So unless until you show the program, it's very difficult to comment that what was the problem. You can come to the department. You can mail me definitely the program.
Okay, sir.
Okay, I can help you out during any other times.
Okay, thank you, sir.
Okay.
Okay.
Others? Any other questions, Tamalda?
No, I think there is no other question. Okay. I have a simple question.
Yes.
Now we are finding that there are computers which are coming with multiple ports.
Right.
So is it possible to use this feature to learn parallel computing for the people in general? Or we need the big computers? Because if you try on the small machine, then we can go for the big machines.
Actually, there are some simulators also you can use for, but in the code is not processor itself. There is a difference between code and processors. Code means that under the same control unit, you have multiple functional units only, like ALUs, you have multiple. But the operating should be in that way that it will schedule multiple instructions, so to achieve the parallelism. So if you, in your new laptops, if you install XP, that will not work. So Windows Vista onward, in Windows based systems, Windows Vista onward, that feature was changed by Microsoft.
Okay.
So lot many issues are there altogether.
Okay. And again, we have a problem like some of the research scholars, they have also problem. In our university, we have this HPC. Okay.
Right.
So they might take your help to run their programs. Okay.
Right.
So in future, I will expect that they will have a contact with you. Okay.
Yes.
And
now the responsibility.
Email address contact is in the university website, particularly those research scholar who want to use. Okay. And they are facing the problem, they can mail me.
Yes, and that responsibility is now under the control of the system manager. Okay.
Okay.
I have taken lot many user IDs for my students of individual batches.
Okay.
And I log into the system with each and every user. I delete everything when I start each and every batch with the same user ID and password. So I don't take every time. I have taken slot wise, 30 for MCS and 20 for MSc. So 55 like that user ID I have already taken.
Actually, I think for computer science, they won't have much problem, but particularly physics, chemistry, they might have small problem because they might have learned how to write a program, but running part actually. So in future, we can have a small hands-on experience if possible.
Definitely.
Just suppose someone has written some program, how to now, because as I have understood, for different HPCs, the commands may be different.
Yes, it will differ. From one operating system to another operating system, one compiler to another compiler. That will differ. Somewhere MPI runs, somewhere MPI EXE.
Yes. Okay. Let us thank the speaker for this taking so much pain in giving such a talk. I will request Arinda Mukherjee sir to give a vote of thanks.
Yeah, thank you very much, Dr. Arjundu Mandal, for delivering such a beautiful talk and illuminating talk before us. And I hope the students are benefited the best. And before concluding, I would also like to thank all the listeners, those who have already joined in this session, and because they are joining their participation make this program very vibrant and also very interactive. With that, we will try again and again to hold such type of meeting where new technologies, new computational skills, or anything that will benefit our computational research scholars, computational demand, and will enrich themselves. And in this case, I also congratulate Dr. Mandal for extending his support and by joining and delivering a talk in this platform. Thank you all. Thank you for today.
Thank you to all the participants and the organizers again for allowing me to give a lecture on this platform with to interact with you all together at least. Thanks to all of you.
Okay, then we'll leave the meeting. Thank you to all.
I'm stopping the recording.
Okay, stop it.
We can have discussion, no problem. Okay, I'm just stopping the recording. And if anybody has something to say, they can say. Okay, and in future, what type of topics or talks we can arrange? They can also write in the chat box. And I have shared one feedback links. Okay, share your feedback using that feedback link. It is in the chat box. I think it is almost 8:28, and we can finish the talk.
Yeah, let's finish. Let's finish it.
Okay.
Okay. Let's leave.
Thank you, Aditi Sarjan. Okay.